All right, so continuing where I left off when my video quit, not independent means we would draw two marbles from that same bag without replacement, which means I take one out. Let's draw it as I go. Take one out and it's either black or white. That's still the 3/5, 2/5. And that's my first marble. And then I don't put it back in. Oh my goodness. So the second marble still might be black or white, but the probabilities are going to change depending on what happened on the first draw. So I'm going to use my thumb to cover up some of these. If I draw a black, then what's left is not 3 blacks and 2 whites, it's 2 of each. So I'm going to label these as 2/4 and not reduce it because I want it really obvious that it's 2 marbles out of 4. Reduce it if you want to, but that's where that comes from. If I happen to draw a white on the first try, then one of these is gone, and what's left is 3 blacks and 1 white. So that would be 3/4 chance of getting a black on the second draw, and 1/4 chance of getting a white. What's happening here is that these probabilities changed based on what happened on the first draw, which means they are not independent. Or you could say dependent in this case because this probability depends on whether I got black the first time or whether I got white the first time. So again, we could find the value, the meaning and the value of each branch. We could find the probability of black and black by multiplying 3/5 times 2/4. Here's where you might want to reduce a little bit. I'll do it unreduced first. It's 6 out of 20, and that reduces to 3/10 or 0.3. I'm going to do that with all the other ones. Feel free to pause the video and do it on your own if you think you know how. Black and then white would be 3/5 times 2/4. Oh, that's the same. What do you know? Not always. Just this time it happens to be the same. This is the probability of white and then black, which is the 2/5 chance of getting white on the first draw times the 3/4 chance of getting black on the second draw. That's also 6/20. Big surprise. But the last one's not going to be 6/20. I can tell already because 3 plus 3 plus 3 is 9. I only have 1/10 left. So this last one's going to be 1/10. But the reason why is because it is 2/5 times 1/4, which is 2/20, which is 1/10. That is my probability distribution, and I want you to notice that it changed because I did it without replacement. And then again, I could add branches together if I needed to, depending on the problem. One more thing I want to say about this tree, and then we're going to write down the official multiplication rule. The multiplication rule says you can multiply branches, but I want to point out that these branches are not just ordinary probabilities, or maybe I should say these first ones are. This is just the probability of getting black. That's where I got the 3/5 from. This is the probability of getting white. So those are easy. This is not just the probability of getting white. It's the probability of getting white given that I already got a white. And I could do that with all of them. This is the probability of getting black given I already got a black. The probability of getting white given I already got a black. I could write that for all of them, but I think one is enough to illustrate it. This is an ordinary probability over here. Actually, both of these are. This is a conditional probability, which is what we were learning about in lesson 5.3a. This is the probability that depends on the one before it that changes because of the one before it. So a few more things to notice. These add up to 1, these add up to 1, these add up to 1, but they're not the same. It depends on what happened first. It determines the probability of what happens second. So that's why this list came out looking different than that list. It made a difference which one I drew first. So that idea of multiplying this times this to get that, actually I just realized there's a typo, or not a typo, I didn't type an error right there. That's a W and W. That doesn't look very good. I'm going to make it look better. And this is the general multiplication rule that we're about to write down and put it in a box. It says that you can take A and B and find its probability by multiplying the probability of A, that's the first branch, times the second branch, which is not just the probability of B, but the probability of B given A. This works for any two events, and that's why it's called general. General means it works for any two events. However, you also could write a special one that's for independent. If A and B happen to be independent, I don't think we've written this down yet. The official definition of independent is that the probability of B given A is the same as the probability of B without being given A. Actually, I think we did write that down. It was in 5.3 A maybe, or I don't know. Anyway, that's the official definition of independent, that the given A does not make a difference in B. If that's true, then you can replace the second one with P of B. So instead you would do this and just multiply the two probabilities together, which is what we did on our independent examples up above. We multiplied probability of a head times probability of a head, and we didn't mess with the givens because given didn't matter. On this one, we multiplied probability of a black times probability of a black, and they're the same probability twice, and we just multiplied it. It was easy. Or they might not be the same. It might be black and then white, and you just multiply them without worrying about it because these are the same as these. If they're not independent, then this one's different, but you still can multiply them. So this is the special case that only works for independence. This is the general case that works for everything because sometimes this happens to equal that. And then I want to point out one other cool thing about this formula, and then we'll do maybe one more example. So one other cool thing about this formula is, look at this lovely equation. A little bit of algebra. Let's rearrange that thing. If you rearrange it to get B of B given A by itself, so a little bit of algebra on this. If I want to get this by itself, it's being multiplied, so I would divide that, and I would get this thing divided by this thing. And you've seen this before. Do you recognize it? I hope you do. It should look familiar because we wrote this down as this is the both over the given, and I told you to memorize that. That's the definition of this conditional probability. So let me finish writing this, and then I'll explain further. I just didn't think I could spell probability right while talking. So some books do this first and then derive this from it. Other books do this first and then derive this from it. It doesn't matter which one you do first because they are equivalent equations based on algebra. So I taught you this one first because it's intuitive looking at a two-way table to use this formula. And I can't remember which direction our book actually does it in. I might have done it the other way from the way the book does it, but it doesn't matter. These are the same. They mean the same thing. And then if you just arrange it in this form, it's called the multiplication rule. If you arrange it in this form, it's called the definition of conditional probability. So now I really want to do a real life example that's better than the marbles and the coins. Last example, 93% of teens surveyed use the internet. I think this is old information. I feel like it might be higher in 2020 than it was whenever this data was gathered. But we're going to go with it. We're going to use the data that we have from whatever year this was. All right. And then also 55% of the teens who use internet which is not all of them, of course, also use social media. And again, I think that number might be higher nowadays, but we'll, like I said, stick with it. So they surveyed these people, asked, do they use internet? Yes or no? And if they used internet, they asked them, do you use social media? Notice this piece of the teens who use internet, that's the given piece because we're dealing with a conditional probability. And then this is the event of interest or whatever you call it. So I'm going to say, here's my tree, internet, not internet. Let's use the correct symbol for that. 93%, 7%. If they don't use internet, what's the chances they use social media? None. You can't use social media unless you have the internet. So this is a 0. This is 100% of the people who don't use internet also don't use social media. Because, you know, smartphones, that's the internet too, in case you didn't know. All right, so this is the more interesting branch up here. If they use internet, social media versus not social media, that's the 55% that I gave you. And this is 45% because that's what makes it add up to 100. These also add up to 100, but they're very different from these. All right. So then if I asked you to find the probability of the internet and social media, that's this branch, you would multiply those together. You would do the probability of internet times the probability of social media given they use the internet. And to me, it helps to write it in symbols, and it also helps to say it out loud in words. So internet times probability of social media given that they use the internet, that helps me. And then we're going to multiply. To multiply percents, you need to change them to decimals. So 0.93 times 0.55, and that comes out to 0.5115 or 51.15% of all teens in the survey use social media and the internet, both. So that's an example of using it for a real situation where this depends on this, and so they are not independent. And this given information was a conditional probability. It's the probability of social media given the internet. And we'll talk some more about that in 5.3c. The main reason you would use a tree is if you're given this type of information. And that's in the next lesson, so I should stop.